is nothing special, really. The week after that is the exam, so I start thinking about common number 2, but we've got like 12 days for that. All right, so this is where we were last time. We were in the middle of improper integrals, so a bunch of stuff to do today. And we're going to start off by just finishing the last little bit regarding that type of discontinuity. So I had written this down last time that if I have infinite limits in both spots, top and bottom, I can't use a single variable and apply to both of them because it could have been approaching things in a different way on both of those different ends. So what we do instead is we have to just break it up somewhere in the middle. Doesn't actually matter at all where in the middle, and solve 2 little baby integrals, improper integrals. One from negative infinity to that spot, the other from that spot to infinity. Okay. So let's do an example like that. These are a little bit lengthy because, well, it's just twice the amount of work. So suppose I had 1 over 1 plus x squared dx, and I wanted to integrate that from negative infinity to infinity. Actually kind of a famous curve. Looks kind of like this. At x equals 0, it's 1. And then it kind of dies down to the axis in both directions. Comes up a decent amount of time. So is there area under that curve that's finite, or does this improper integral diverge? So there's no reason to choose anything other than 0 usually. So I'm going to choose my division breakpoint to be 0, and I'll go from negative infinity to 0 of this 1 over 1 plus x squared dx, plus the second one, 0 to infinity, 1 over 1 plus x squared dx. The only time you might not choose 0 is if the antiderivative was something where there was maybe an easier thing to evaluate. I don't know, suppose it was like powers of like x minus 1 to the 3 halves or something like that. If this was the integral from negative infinity to infinity, I guess that even wouldn't work. It's undefined at 1. So yeah, it's very rare that you wouldn't choose 0. Let's just stick with that and make it simple. So I'm going to set this up. I've got to take care of both infinite limit parts. So I'll say limit t approaches negative infinity, the integral from t to 0 of 1 over 1 plus x squared dx, plus, now on this side I don't want to use the same letter because it's already been used in the problem. So I'll just pick something else. So like I said, we're going to have to use a different letter here to represent this one since it's a different variable. So it just doesn't matter what you call it. I'll say w, which is infinity of 0 to w, 1 over 1 plus x squared dx. Simple antiderivative, it's going to be inverse tan. It's going to be an inverse tan, so we get limit as t approaches negative infinity of tan inverse of x from 0 to t, plus, obviously it's the same thing on the other side as far as the antiderivative goes, so you don't have to integrate it twice. Limit as w goes to 0 of inverse tan of x from 0 to w. So then we can plug all those limits in, still with these limits as t goes to negative infinity and w goes to infinity on the outside. So I get tan inverse of t minus tan inverse of 0 plus the limit as w approaches infinity of tan inverse of w minus tan inverse of 0. Okay, so let's evaluate these things. Now, tan inverse of negative infinity. Let's see if you guys...
Professor.
Yeah?
Quick question. The limits, are they both going to go from 0 to c? Like for the first one, you have tan inverse x from 0 to t, and then the other one is also from 0 to w.
Oh, good question. So it should be t to 0. I just switched them right here, right? On this one step. This should have been from t to 0, right? From negative infinity to 0, and from 0 to infinity. And it's correct. Oh, I have it written backwards here, right? Okay, thank you for that. So I have to subtract these in the other order. So tan inverse of 0 minus tan inverse of t. Yeah, okay, appreciate that. So now when we plug in, we have to figure out what is tan inverse of 0. So do you guys remember that from trig? What is tan inverse of 0? It has nothing to do with the limit here, it's just a straight thing. It is 0, right? Because tan 0 is 0, so tan inverse of 0 would give you back to 0. Harder one maybe. What is tan inverse of negative infinity? So what angle has a tangent of negative infinity? So we're basically asking here of negative infinity is saying basically tangent of what angle is equal to negative infinity. Not 1, because we know that tangent pi over 4 would be equal to 1, right? So if I said tan inverse of 1, that would give me pi over 4. 2, no. So let's consult the tangent graph, right? If you remember the tangent graph, it looks like this. Its primary piece of it anyway, primary period. And it has asymptotes here. And if you recall, obviously it goes through 0, 0. And these asymptotes are at plus or minus pi over 2. All right, so where in this graph does the tangent function go to negative infinity? And the answer is, in the limit anyway, at negative pi over 2. So this piece here would be negative pi over 2, tan inverse of negative infinity in the limit. Okay, now plus, now we can kind of see the answer for the other one. Tan inverse of infinity in the limit is going to be pi over 2. And minus tan inverse of 0 again is 0. Notice, by the way, just the nature of this, you have a plus tan inverse of c, whatever you chose c to be, and a minus tan inverse of c on the other side. So these two pieces will actually always just cancel out. You don't even really have to evaluate them. You can just note that those two cancel out with one another, and then you just have the two endpoints. So in the end here, we get positive pi over 2 plus positive pi over 2 for a final answer of pi. There's exactly pi area under that particular curve. Okay, so I'm going to erase this, and then we'll get to the second big case of improper integrals, which is discontinuities at the limit in the function. So call this case 2, which is discontinuities in the function f of x at a limit. And again, like I said, it gets a little confusing because there's the limits that we're taking and then the limits, of course, in the integral bound problem. So what this is saying is, in your limits of the integral, 0 to 5 or whatever, f of x is discontinuous at one of those places. And it's actually the same exact strategy. So I'm going to say it's the same strategy. We're going to say, let's just get closer and closer and closer to the limit, which is the problem spot. And then we'll do the integration and then take the limit after we're done. So same strategy. Basically taking the limit as we approach the problem spot or the problem limit. However, this one gets a little bit harder for people for two different reasons. Number one, it's not so obvious, right? If I was looking at, let me just give you an example. If I was trying to do the integral of 1 over x minus 1 dx, and my limits were 2 to infinity, almost no one messes this up because they see the infinite limit. It's obvious, okay, I have to do improper integrals. However, if the limit were 1 to 5, people miss this all the time because the problem is the fact that the 1 is discontinuous in the function itself, right? So it's easier to miss in that case. The second reason it's harder is because in the infinite limit case, there's only one way to approach infinity or negative infinity, right? I'm going off to infinity or off to negative infinity. However, if I have to approach a problem spot at 1, I have to say which way I'm coming from. You have to go through those left and right limits that you learned about in Calc 1. So I'm just going to say we need the left-right limit notation when we're doing any of these problems. Okay, so here is the summary of all the notes, and then we'll do some problems. So for f being continuous on, let's say, A to B, so notice closed interval A, open at B. So f is perfectly fine, but at the second limit, the upper limit basically, there's going to be a problem spot. So if we wanted to integrate a to b of f of x dx in this case, but b is not continuous, and or the function is not continuous at b, we'd have to say, let's let a variable, call it t, approach the problem spot b, all right, there's one piece I'm missing there, and then integrate from a to that variable, a to t, of f of x dx. However, in which direction are we approaching b? Because b, right, imagine you've got something like this. If this was x equals b, it could make a lot of difference if I'm trying to take the limit as I approach b from the left, or if I approach b from the right. So in this case, if I'm integrating from a to b, I'm clearly approaching from the left. So it's going to be a left limit notation. And if you're confused, it's just easy to draw out on a number line your a to b, and then you can see which way you're approaching the problem spot. Let's look at the other cases, though. It's 3 of them. So if you had f continuous on open interval a at the bottom, closed interval b at the top, then if I wanted to integrate f of x dx from a to b, now I've got to approach the bottom problem spot. So it's the limit as t approaches a, this one from the right, here's my interval from a to b. This is my problem spot at a, and I'm approaching along that interval, I'm approaching from the right. So it's a right-hand limit. And then it'd be an integral from t to b of f of x dx. Third, for f being continuous, so in that case, what you'd have to do is you'd have to split up, again, the integral from like a to some point c, and then c to b, and do 2 little baby ones. The one actually I want to talk about is f is continuous, except in the middle. So it's continuous except at c on the range a to b, but c is in the middle of a and b. So what this is saying is something along these lines. Imagine I'm integrating from a to b, but there's a discontinuity at some middle point. So maybe it looks like this. So what you're going to have to do in this case is say, all right, well, I've got to integrate from a to c. So that would be basically like the first type of limit. And then I'll integrate from c to b and add them together. That second one would be like this second type of limit. So just like a double amount of work, but it's a doable problem. So ultimately, the integral from a to b in this case is going to be equal to this. Integral from a to c of f of x dx plus the integral from c to b f of x dx. And then you solve these 2 smaller improper integrals. All right, so obviously we're going to want to see a little bit of this stuff in action. So I'm going to do a couple, I'll give you a couple, and then I think we can say that we've got improper integrals down. Okay, so I'm going to erase this. And do, first of all, a pretty easy example. Suppose I have the integral 0 to 1 of 1 over root x dx. So you'll notice, and this should be now becoming a habit, whenever you see a definite integral in this class or going forward, you should check to yourself, is there any problem spots? Well, first of all, is there infinite limits? That should be obvious. But is there any problem spots in this integrand on the range over which I'm integrating? And here you can see I'm undefined at 0, so there's clearly a problem spot in this range. So I'll just note that this is undefined at the bottom limit. All right, so just again, quick note, if you had integrated this thing from like, I don't know, say 0.5 to 1, you wouldn't have to worry about it, right? There's a 0 undefined point, yes, but it's not in the range, so just proceed as normal. Some people ask, what does this mean for the antiderivatives, right? If there were no limits at all, I could get an antiderivative of this. Well, like, what's the meaning of that function if sometimes it works and sometimes it doesn't? Well, it's implicit in the antiderivative notation that it's only true if f of x was continuous. So if you're looking at a range where the limits wouldn't make it continuous, then you've got to obviously say I'm discarding that antiderivative. It doesn't make any use. All right, so anyway, in this case, we're going to have to integrate. But first of all, let's set up our improper integral with a variable t as we're approaching 0. And again, here's my range. I'm approaching from the right, so it's going to be limit as t approaches 0 from the right. Integral from t to 1 of 1 over root x dx. Simple integral in this case. Rewrite the limit though. It's just x to the negative 1/2, so power gets increased by 1, so root x. Divide by the new power of 1/2, so division by 1/2 is 2. And we get 2 root x evaluated from t to 1. Then we can plug it in. So 2 root 1 minus 2 root t. And we can see that if I now plug in and evaluate my actual limit, 2 doesn't make any difference. T has to go to 0 from the right. It's going to actually be really important if I'm coming from right or left. You're going to have to be really careful in this case. Plugging in 0 in this one doesn't actually make much difference, but we'll see where it does later on. If I was coming 0 from the right, that means I'm getting to be like very small numbers that are positive. So square root of a positive number very close to 0 is 0. So that's actually your final answer. So this integral converges to 2. Technical point, just on the side. What's the limit as t approaches 0 from the left of 2 root t? What would this answer be? Okay, so people are putting some imaginary numbers. That's true. Generally in calculus, we're just going to deal with assuming things are real numbers. Imaginary numbers we'll leave if you're taking a complex variable class. But basically what you would say in this class is, look, this is basically a negative underneath the root here. So a negative is undefined in a root, so this does not exist. So you can see the direction actually is going to cause a huge difference here. How about this? Integral 1 to 2, 1 over x minus 2 squared dx. So problem spot you can see is x equals 2 is undefined. So that's the top limit. So it's an improper integral. T approaches 2 from the... For some reason, I'm very bad with left and rights. I don't know why. So I always just have to draw the interval out. And I say, all right, I'm approaching 2, and that's coming from the left. I'm sure a lot of you guys are better with your lefts and rights than I am. Might skip that step. So anyway, integral 1 to 2 of 1 over x minus 2 squared dx. Technically, this is a little u substitution, but it doesn't really matter because du is equal to dx. So I'll just integrate it as if x minus 2 is my variable. So I'm going to raise the power by 1 to negative 1 and divide by the new power, which is a negative 1. So you should get negative 1 over x minus 2 from 1 to, wrong limit here. Should not be 1 to 2, should be 1 to t. So evaluate that from 1 to t. I get a limit as t approaches 2 from the left of, plugging in t, I get negative 1 over t minus 2. Minus is a plus, 1 over 1 minus 2. And this is, again, we have to be really careful here because of the evaluation as approaching 2 from the left-hand side. So what does that mean for this denominator? So as I'm approaching 2 from the left, I'm getting very close to 2, but numbers that are like 1.99, 1.999, 1.9999. So what does that leave me here? Something very close to 2, but a little less than 2, minus 2, gives me something like negative 1 over, I'm going to just put like a negative 0. Because it's going to 0, but it is a negative sign. A plus, this is going to be 1 over negative 1, so that's just a negative 1. But that's actually not going to matter, because what happens here? What's a negative 1 divided by a negative tiny number? Well, two things to keep in mind. The sign will be positive, because it's negative over negative, and 1 divided by something tiny is huge, so this goes to positive infinity. So the answer here is infinity, and the integral diverges. So there's some subtleties here in being very careful with the direction of the limit and evaluating it very carefully. So let's, I want to see if you guys have any questions with that.
How do you get the negative 0 in the denominator again?
Okay, so when I plug in this limit as t approaches 2 from the left-hand side, right? So from 1 to 2, I'm approaching 2 in this direction, right? So what numbers are these values of t? They're numbers that are close to 2 but less than 2, like 1.99, 1.999, etc. So when I take one of those numbers and subtract 2 from it, you can see I'm going to get a negative number. But since it's approaching 2, it's going to be approaching an infinitely small value, but it will be a negative, very small value. All right, I'm going to do half of one more example, but then leave the rest of it to you, because it gets very long and tedious. But if you had the integral of something like 0 to 2, 1 over 2x minus 1 to the 2/3 power, dx. This one's the most difficult to see and the most amount of work, so it's kind of the hardest problem because it's sneaky. The endpoints are perfectly fine, they're not undefined, but there's an undefined point in the range over which I'm integrating. So this is undefined at 2x minus 1 equals 0, or where x is equal to a half. And that is in the range of integration. So I have to deal with it via improper intervals. So the only way to do it is to go from 0 to there, and then from a half to 2 in 2 different integrals. So this is going to be the limit as, let's say, t approaches 1/2, the integral from 0 to t. And in this case, are we approaching from the left or the right? I'm just going to write it out. There's my interval. So from 0 approaching a half, that's from the left. And I'm integrating 2x minus 1, 2/3 dx, plus the second one is the limit. And again, I need a new variable, so I guess I'll call that w. W approaches 1/2. It's pretty safe bet to say it's from the opposite side, from the right. Integral from w to 2 of 1 over 2x minus 1 to the 2/3 dx. Let's just double check the direction. If I'm going from 1/2 to 2, that's my range, then my limit is going to be approaching on this range, so therefore it's coming from this direction, and that is from the right. All right, so I don't want to go through all the work because it's very messy in this one and rather long, but for those that want some extra practice or just have been a little rusty with algebra and or Calc 1, I will give you your final answer here. So you can check it out at home if you wish. Well, I guess you are at home, but in your own time. 3/2 times 1 plus the cube root of 3 is what you'll end up with in this case. Okay, so I'm now going to give you 2 problems to try that are a little bit easier than the one that I just wrote down. So you can really choose your own adventure here. You can do the 2 that I'm giving. If you want to work this one out and see if you can get to that answer, that's fine too. But for the purpose of learning how to do these improper integrals, I'd recommend doing these 2 first. 1 over x root x dx from 2 to infinity. And the second one for you is negative 8 to 0, 1 over x to the 4/3 dx. Guess I'll give you the answer. This first one is going to converge to root 2, and the second one diverges to infinity. So those are your answers. Let's take 10 minutes or so. Integrals should be easy, but just make sure you get the setup, the familiarity with how the improper stuff works. I'm going to go find a cat to show you. Any requests? Monty, Luna, or Andy? All I don't know. Although that is the common favorite. Oh, you want to see the rare Andy cat? Okay. You might not have seen Andy. Andy's such a floof. Just satisfy Nicole and Jason, though. Here is all. Hanging out. Let's find Andy. Andy cat. I got bad news, good news. She's in a spot that cannot be disturbed. However, we'll do a class trip. Andy. Want to see your floof? Look at the floof tail. There you go. And a bonus. Yeah. Yes, we have a lot of floof around the house. I can actually just let me just reach down on the floor right now, right? I just randomly, yeah, there's hair all over the place. Visible clumps of hair. Mr. Monty, were you left out? Were you left out? All right, let me see. I wrote the wrong answer down. Well, 2 over root 2, you should simplify, right?
Professor, I have a question.
Yeah.
How do you know whether the limit's going like a positive or negative? Is it because like if it's like the second number, so if it's like negative 8 to 0, that 0 is going to be positive?
Well, don't think of it as positive and negative. You do positive and negative sign to denote it, but think of it as if from the left or from the right. So if here's your interval, right? Negative 8 to 0. So I'm on that interval. In which direction would I be approaching negative 8? This way, right?
Yeah.
So then it's from the right.
Okay. Thank you. So I was thinking them like as positives and negatives because of like negative infinity, positive infinity.
Nothing has, yeah, that's nothing to do with the sign of the number, just from the left or from the right. The reason they use positive and negatives is if you look at a number line, right? In general, if you're approaching from the right, you're coming from the positive numbers side of things. If you're approaching from the left, you're coming from the negative numbers side of things. But it doesn't have to be, I mean, the interval could be on one side only, or all sorts of intervals. All right, one more for you guys. There. Andy's the middle one, yeah. How do they get up there? I mean, they jump. They're athletic. Except for Andy, I put her up there. She's not athletic. All right, so I'm gonna move on. If you didn't get these, either try later, or you can check with me at the end of class. I can stick around, but they should be relatively straightforward. Now we're going to come to, I don't know if we'll finish it all. No way you're going to disrespect Andy like that. Honestly, saying not athletic is kind of putting it mildly, but poor Andy. We're going to come to this interesting topic, which is the last thing on integration for a little bit. It's called convergence comparison tests. This is going to be a huge skill for the next group of stuff on sequences and series. So we're going to learn it first in the context of integrals, but this is going to be really important soon enough. It's going to be one of the most important things for exam number 3, the concept of it anyway. So here's the idea of a direct comparison test. It says, suppose that f of x and g of x, two functions, are continuous on the range, from a off to infinity. And we also know that basically the functions are always positive, at least on this range. And we know that g of x, one of the functions, is always bigger than or at least equal to the other function. So I don't want you to memorize anything here. A lot of people do. It doesn't really help you. I want you to understand why the results of these several statements we're going to make are true. Suppose that we've got the integral from a to infinity of g of x dx. All right, that's the bigger one. And we know that that converges. Okay? Then, does that mean anything? And I want to draw a picture up here of what these functions might look like. So imagine for a second, here's a to infinity. I've got two functions. G of x is always bigger than f of x. So here's g of x on top. F of x, it could go up and meet there, but it's always at least under or at the other one. So what we're saying is if the area under the curve of g of x, the top one, if that area is finite, it converges. So imagine like the area under g of x is 10. What do we know about the area under f of x, if anything? Think about the logic of it. It's got to be less than 10. It's got to converge as well. So then we know that the integral from a to infinity of f of x dx also converges. And I'm telling you, there's going to be people in a lot of Calc II classes that are trying to memorize all these different conditions. But there's nothing that needs to be memorized. It's just simple logic if you understand what's going on. Second thing, if the integral from a to infinity of g of x dx diverges, right? So that says the area under the curve of g of x is infinite. What do we know, if anything, about the area under f of x? That's for you guys. So infinite area under g of x. What do we know about the area under f of x, if anything? All right, so the tempting thing is to say it also diverges. You guys agree with that? So if there's infinite area under the top one, does something smaller than it have to have infinite area under it? It doesn't have to, right? This one could have infinite area under it, but this one could have maybe 2, right? It could have an area of 2 under it. That's less than infinity, so that would be valid. It could have infinity, right? It could also diverge, but just a little bit smaller divergence. So in this case, you have no idea what happens to f of x. It just doesn't tell you anything. So in this case, you would conclude nothing. I'm going to go through the other two, and then I'm going to circle back to see, do you have any things that you want to go over again? Because I'm sure some people will. Third, let's look at the smaller one. Suppose we know something about the smaller one. If the integral from a to infinity of the smaller one, f of x, if that diverges, so there's now infinite area under the smaller one, does that tell us anything about the area under the bigger one? It has to be infinite, right? If the area under here is more than infinity, well then obviously it's infinity. So then the integral from a to infinity of g of x dx also diverges. And then the last one, suppose the integral from a to infinity of f of x, the smaller one, converges. What does that tell us about the area under the bigger one? Nothing, right? So this converges, imagine the area under here converges to 2. Well, the bigger one could go to 4, or it could go to infinity, who knows? So in that case, you conclude nothing. So last time I'll mention this, but people try and memorize these cases, and believe me, when we get to sequences and series, there's so many tests and all these different conditions, you'll get all of them turned around and confused if you try and memorize them. But logically, you should be able to, with, thinking about it for a few minutes here, accept and see that this is kind of obvious once you start getting used to this, right? If you know which one's bigger, you can know if you can tell something or nothing about the other ones, and vice versa if you know something about the small. I don't think we're going to get to the limit comparison test. I forget if this section has 2 homework assignments or 1. If it has 1 homework assignment, it will be due on Wednesday. If it has 2, the first one will be due on Sunday like normal, and the second one will be due on Wednesday. Okay, so here's some examples with direct comparison tests. Determine if the integral from 1 to infinity of sine squared x over x squared dx, determine if that converges or not. Now there's a very big hint here where they do not just say evaluate this integral. They say just does it converge or not, which means you do not have to find the answer. You may not even be able to find the actual answer. It just says, basically, without saying it, use a comparison test to see does it converge or does it not converge. And then that's all you have to give. So in this case, it would be a very difficult integral. I don't know how to do that integral. If you were to try and think about it, you'd get stuck because it's quite difficult. But we could say that it's always positive. So it's going to pass the first condition of the direct comparison test. Say it's just squares. So sine squared x over x squared is always greater than or equal to 0. Is there something that I can compare this to, which I know how to integrate? And I know that sine is bound between 0 and 1, right? So the square of something between 0 and 1 is also between 0 and 1. So I know that this is also between 1 over x squared and 0. And that's the biggest it can possibly be at any moment. Sine squared's biggest value would be 1. So what we're going to do, and this would be true on the range 1 to infinity, what we're going to do is let's just do the integral from 1 to infinity of 1 over x squared dx see if that works into something useful and see if the direct comparison test actually works. So integrating this is no difficulty, but we do have to make it an improper integral. So let's do that first. So this is the limit t approaches infinity, 1 to t of 1 over x squared dx. As it stands now, you guys have no partial credit on the exams, but if you're doing this on a quiz, or if you're doing it during a normal semester, if you don't make this an improper integral, you're going to lose hefty amounts of points, because that's the whole point of this section. So we get limit t approaches infinity of negative 1 over x from 1 to t, which is limit t approaches infinity, negative 1 over t, minus negative 1 over 1. So what happens here? 1 over infinity goes to 0, so that term goes away. Minus minus is a plus, so I get 1. By the way, somehow if you screwed up your signs on this and you got a negative here, you could have immediately said, I know that's wrong because I knew that this function is always positive, so the area under the curve has to be positive. So basically this thing converges. Now, I know that sine squared x over x squared is always less than 1 over x squared. Therefore, it has to converge as well to something a little less than 1. Right? So this integral has to be less than 1, therefore it has to converge. So I can say that since sine squared x over x squared is less than or equal to 1 over x squared, the integral of sine squared x over x squared from 1 to infinity dx must also converge by, we'll use this acronym that I noted, DCT for direct comparison tests. Now, some people mistakenly say that this integral also converges to 1 by DCT. DCT does not give you what it converges to, right? It actually will not converge to 1 because it's less than 1 on this interval for sure. So it's going to converge to something we do not know what it is, but we do know that it's less than 1, and most importantly, we know it converges. So we've answered the question, it does converge, and we use direct comparison tests to do it. All right, so I'm going to give you a general rule and then do another problem. So in general, if you have an integral from, let's say, some value to infinity of 1 over x to the p power, it turns out since these things are very easy for us to integrate, we use them for comparison tests quite a bit, and we don't really want to have to integrate over and over and every single time. This thing converges if p is greater than 1, and it diverges if p is less than or equal to 1. And we call this thing the p-test. We're not going to prove it right now. It's actually pretty easy to prove. We're going to prove it in the next sections when we do it with infinite series and infinite sequences. You could see that this kind of makes sense just by hand waving, right? If you get something like a very small value, like even negative, if p was a negative number, then it's just going to be an x in the numerator. So that's obviously going to diverge, right? The integral of x squared, the thing is growing. So you've got to at least die down to have a chance of converging to something. But we don't know exactly why it's this specific spot, x equals 1, which makes us be the borderline case between there's infinite area under that curve to going to there's actually finite. But we'll prove that when the time comes. Okay, so any question? Guess there's really no question with that. Didn't really prove anything, so let's do the next one. Okay, so determine if this integral from 1 to infinity of 1 over root x squared minus 0.1 dx converges or not. Again, the wording of the question, the wording of this question implies that I don't actually have to evaluate the integral and find the real answer. I'm just interested in, does it converge or not? And for many mathematical applications, that's really all you need. So what we'll see is that in such a case, I'm going to make a comparison test, and the obvious thing to compare it to, the first guess, is just drop the lower order terms. Everything should always behave like the largest order terms. So if I drop the lower order ones and compare to that, it should work the same way. So I'm going to say as like a rule of thumb, I'm going to drop the lower order terms and compare to the result. And I'm going to call this result like the natural comparison to make. The last problem we did didn't really have a natural comparison. It was what, sine over x squared. There were no lower order terms. The highest order term in the numerator was the numerator. Same with the denominator, so we have to be a little more creative. Here, the lower order term is the 0.01. So I'm going to compare to the integral from 1 to infinity of 1 over root x squared dx. And that should behave the same way as the original. You can see that this is equal to 1 to infinity of just 1 over x dx. Now, instead of having to do an improper integral in this case, we can note that it's in the form of the p-test. So I can just, at this point, memorize these conditions. Later we'll know why they came from, and get the answer to this comparison integral very easily. And we can see that p is equal to 1, so that's part of the divergence case. So p is equal to 1, so this diverges by the p-test, since p is less than or equal to 1. When you are proving this stuff out, you have to say 3 things for every little proof piece. You have to say what it does, what tests you're using, and what's the condition of the test. So this diverges. Right? Now, let's compare 1 over x to this piece here. So if I looked at 1 over root x squared minus 0.01, and I was comparing it to 1 over root x squared, which is just equal to 1 over x, which of these two is bigger, left-hand side or right-hand side? Okay, let me ask you this question. Which is bigger between these two numbers, left or right? 1/2 or 1/3? Left, 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 right? With the numerator being the same, the bigger denominator makes it smaller, right? So same thing here. These numerators are the same. Which is the bigger denominator? This one, that makes this side smaller and the left side bigger, always. I guess I put greater than or equal to, but that's basically the thing there. So a lot of people see the negative sign and get it the wrong way. It's in the denominator, so it's working the opposite direction. So you have to be careful when you make these comparisons that you make the algebraic comparison part correctly. So for all values of x, this will be the bigger side. So now I have to go back to say, what does this do? This one diverges, and this one is always bigger than that. So if this goes to infinity and this is bigger than it, it also has to diverge. So I'm going to say, since the integral from 1 to infinity of 1 over x dx diverges, then the integral of 1 over root x squared minus 0.1 dx going from 1 to infinity, that also must diverge, I guess I could say, to infinity by dct. But in fact, it's going to be a larger infinity than the first one, but for our purposes, infinity is infinity, it diverges. Let's see, someone's questioning it. So the comparison we made is smaller than it, right? So the thing I'm looking for is bigger than something that goes to infinity. right? Okay, there we go. And so a lot of times you just have to ask your, like, run through the sentence in your mind, like, okay, this is infinite, this is bigger than it, so if it's bigger than infinity, okay, we're done. If it was the other way around, right, imagine this was a plus sign, and then it would be the opposite way. You'd have like this, you'd say, okay, I found this is infinite, and this is smaller than infinity, so, okay, then I wouldn't know. I could be a smaller infinity, or it could be a 2. So that's the question you want to ask yourself as you go through these problems. Now, I said that this is the natural comparison to make, right? So even if it was like this, the case which it doesn't work, if I was trying to do 1 over root x squared plus 0.1, I would still naturally compare it to this, 1 over root x squared, to something that diverges, and then it would fail. I'd say, oh, the thing I'm looking for is smaller than something that diverges, so I don't know. So the next question we have to ask ourselves is, what if we're in one of those 2 cases, and it happens half the time, just by chance of your problem, what if we're one of those conclude nothing cases? So what if we are in, let's say, one of the 2 conclude nothing scenarios? And for that, we have to do a new test, something called the limit comparison test. It also gets an acronym, and we'll pretty much always just refer to it as LCT. I think, where are we? 344. I think I'm just going to define it, and then we'll pick up from here on Tuesday. But it says, suppose that f of x and g of x, again, are continuous on the same range, let's say, from a to infinity. But I don't really care which one's bigger, because this is going to deal with all the cases where the wrong one is bigger compared to the other. So the approach now is we set up a limit as x approaches infinity of f of x over g of x. Which one goes on top and which one goes on bottom, it actually doesn't matter. You just divide the 2 of them in either order, and you get a limit. If that limit is a number between 0 and infinity, then the integral of a to infinity of f of x dx and the integral of a to infinity of g of x dx behave the exact same way. That means that if you get this condition, it doesn't mean converge, it doesn't mean diverge. This just means that the 2 things do the same thing, whatever it happens that they do. So I'll just say they either both converge or both diverge. We'll talk about it a little bit more next time, but what we're basically saying is that the 2 things are moving at the same rate. So whatever one of them does, the other has to do. Maybe proportionally a little bit slower, a little bit faster, but they're at the same rate, so they end up doing the same thing. I'll just put also here, if L is equal to 0, yes, or infinity, then the test fails. That basically means that the 2 things do not move at the same rate. One of them moves infinitely faster than the other one. So I can't really say if they're moving at the same rate, because they're not. And that's why, by the way, you can divide in any order, because as long as you get a number that's not these cases, you'll get that they both behave the same way. So imagine you divided this way and got a 2. Well, if you divided the other way, you get a half. So any number and its reciprocal would be in the same range. The 2 problem spots would be the 2 cases that are opposite to each other. If you took this limit and divided by each other and you got a 0, if I had flipped it, I'd get infinity. So the 2 problem spots are also reciprocals of each other. So that's why the order doesn't matter of this division. Okay, we do not have time to finish this section, so I don't really want to actually start an example with it. So let's call it a day there, and we'll pick up with how to use the limit comparison test on Tuesday. So usual stuff, quiz on Wednesday, homework due Sunday and Wednesday night. And we'll go from there. No comparison tests will be on the quiz. but it could be anything else we've done. Otherwise, have a good weekend.